Picture this. You're walking through the heart of ancient Rome. The sun beats down on marble temples and crowded forums. Chariots rumble over stone-paved streets. Merchants shout, and the air is thick with the scent of spices and smoke. Life pulses everywhere you look, but beneath your feet, hidden from view, lies another world entirely, a world of profound darkness, of echoing footsteps, of engineering so advanced it defies belief. This is the hidden realm of Roman underground tunnels. Down there, in the cool, silent earth, Roman engineers accomplished what many ancient peoples would have considered impossible. They carved out vast networks, passageways, and chambers, not with simple tools, but with breathtaking ingenuity. These were not just crude holes in the ground. They were precisely engineered structures, built to carry water, to transport troops unseen, to shelter citizens, and to channel the very lifeblood of the empire away from prying eyes. While the glorious monuments above ground celebrated Roman power, it was these shadowy, subterranean passages that often ensured that power endured. What's truly astonishing is the sheer scale of their vision. We often marvel at the Colosseum or the aqueducts stretching across the landscape, and rightly so. But to grasp the full genius of Roman engineering, you must also look below. Imagine the courage it took to venture into that darkness with little more than oil lamps and hand tools. Envision the teams of laborers and architects, armed with nothing but geometry, sheer muscle, and an unshakable belief in their mission. They tackled unstable ground, the threat of collapse, and the ever-present challenge of ventilation and light, yet they persevered. The tunnels they left behind are a testament to a civilization that thought not only in terms of grandeur, but also in layers, building in 3 dimensions, from the heavens to the underworld. They understood that a city's true strength often lies in its foundations, in those secret veins running deep below the surface, unseen but utterly essential. Today, as archaeologists and historians slowly uncover and map these incredible subterranean structures, we're granted a rare glimpse into the Roman mind. This isn't just a story about digging, it's a story about solving impossible problems, about human ambition stretching beyond the limits of their time. In this video, we're going to descend into that hidden world together. We will uncover the methods they used, the obstacles they overcame, and the brilliant innovations that allowed them to build lasting tunnels without the technology we take for granted. You'll discover why these underground marvels remain some of the most impressive and mysterious achievements of the ancient world. So if you're ready to explore the secrets buried for centuries, to walk in the footsteps of Roman engineers, and to see history from an entirely new angle, then let's begin this journey deep beneath the streets of Rome. But to truly understand why they invested so much effort beneath the surface, we need to step back and consider the Roman worldview. This was a civilization obsessed with utility and control, and they saw the underground not as a barrier, but as a resource. Above all, their most pressing motivation was water. A city of 1 million people, like Rome at its peak, consumes a staggering amount of water daily for drinking, for bathing in the immense public bathhouses, for sewers, and for spectacular fountains. Aqueducts are the famous above-ground solution, but their final miles, the critical distribution networks within the city itself, were often sophisticated underground tunnels. These subterranean channels, built with precise gradients and lined with waterproof cement, protected the precious water supply from contamination, evaporation, and even enemy sabotage. It was the ultimate act of civil engineering foresight, ensuring that the lifeblood of the city flowed cleanly and reliably directly to where it was needed most. Beyond public health, there was a powerful military logic to going underground. The Roman army was a master of practical strategy, and they quickly realized that tunnels were a formidable tactical tool. They could be used for surprise. Imagine a besieging army camped outside a hostile city's walls, confident in their defenses. Meanwhile, Roman legionaries, many of whom were also skilled engineers, would be quietly digging a mine underneath those very walls, preparing to collapse them or emerge suddenly in the heart of the enemy's stronghold. Conversely, they also dug defensive tunnels to intercept enemy miners or to create hidden escape routes for their own forces. This underground warfare, a silent, claustrophobic battle fought in near-total darkness, added a terrifying new dimension to ancient combat. It was a psychological game as much as a physical one, creating a constant fear that the ground itself could become an enemy. The drive for resources provided another powerful incentive. Rome's immense wealth and industrial capacity were built on materials extracted from the earth. They constructed vast mining complexes, like the one at Las Medulas in Spain, where they didn't just dig simple pits. They used a technique called ruina montium, which means the wrecking of mountains, employing pressurized water to blast away entire hillsides to reach gold deposits. But to control that water, they first had to build extensive networks of tunnels and channels through the rock. For more everyday materials like stone, clay, and the lime used in their famous concrete, underground quarries were essential. These operations supplied the literal building blocks of the empire, and the tunnels left behind are a stark reminder that Roman grandeur was fundamentally rooted in the raw materials pulled from the ground. Finally, we must consider the spiritual and social dimensions. For the Romans, the underworld was the realm of the gods and the dead. Certain mystery cults, like those dedicated to Mithras, conducted their sacred rites exclusively in underground chambers called Mithraea. These spaces, often small, dark, and windowless, were designed to evoke the cosmos and create an intense, personal religious experience far from the public rituals of the state religion. On a more practical social level, the early Christians in Rome famously used underground catacombs as burial places. While not typically used for regular worship, these vast, labyrinthine networks provided a space for a persecuted community to bury their dead with dignity and to gather in relative secrecy. So, from ensuring a city's survival to winning a war, from extracting immense wealth to seeking divine connection, the Romans had a reason for every shovel of earth they moved. Their world was not just what they built toward the sky, but profoundly and deliberately what they carved into the earth beneath their feet, of course. The incredible structures we've just discussed all began with a single, crucial step. The Romans had to first master the landscape itself. Before a single shovel bit into the earth, their engineers embarked on a meticulous process of reading the land, a skill that combined sharp observation with sophisticated, yet elegantly simple, technology. They knew that a tunnel's survival depended entirely on the ground it passed through. The wrong choice, digging through loose, sandy soil or hitting an unexpected water table, could mean catastrophic collapse or a flooded passage, wasting years of backbreaking labor. So, they became experts in geology long before the term even existed. They learned to identify stable rock layers, like the resilient, tough, and hard limestone found around Rome, which could hold a tunnel shape for centuries. Just as importantly, they trained their eyes to spot the subtle signs of danger, certain types of vegetation that hinted at shallow groundwater, or erosional patterns that revealed soft, unstable subsoil. This intuitive understanding of the earth was their first and most vital line of defense. To translate this knowledge into precise action, they relied on a toolkit that was brilliant in its practicality. The workhorse of Roman surveying was the groma, a deceptively simple instrument that allowed them to lay out perfectly straight lines and right angles across vast distances. Picture a surveyor standing on a hilltop, rotating the cross-shaped arms of the groma. From each arm hung a plumb bob, a weight on a string. By sighting along these weighted lines, he could establish a straight visual path through the landscape, marking the intended course of the tunnel on the surface with posts and trenches. This ensured that crews digging from both ends of a planned tunnel would eventually meet in the middle with astonishing accuracy. But straight lines weren't enough. The gradient, or slope, was everything, especially for water channels. For this, they used the chorobates, a masterpiece of ancient engineering. This was a long, wooden bench, perhaps 20 feet in length, with a carefully carved groove running along its top. The surveyor would fill this groove with water, using the perfectly level surface of the water as his reference. If he needed to establish a gentle, consistent downhill slope for an aqueduct tunnel, he could adjust the chorobate's legs and use the water level to calculate the precise drop over a specific distance. Some sources even suggest they used metal sights for astronomical alignment, making it a multi-purpose leveling tool of remarkable precision. This marriage of observation and instrumentation allowed Roman engineers to plan their subterranean routes with a confidence that still inspires awe. They weren't just digging randomly, they were drafting a three-dimensional blueprint of the Earth itself. By correlating surface features with the data from their tools, they could effectively see underground, predicting where a stable rock layer would be and avoiding zones of weakness. This meticulous planning minimized the need for extensive internal supports, saving an immense amount of timber and labor. It also meant that tunnels for roads or military movements could be driven through hillsides on the most direct path possible, while aqueduct tunnels could maintain that crucial gentle slope for miles, ensuring a steady, reliable flow of water powered by gravity alone. In essence, the Romans treated the landscape not as an obstacle, but as a partner. They listened to its clues, measured its form with ingenious tools, and then respectfully, yet masterfully, carved their will into stone, creating a hidden infrastructure that was as intelligent in its conception as it was monumental in its execution. Once the surveyors had mapped the route, the real work began, a grueling symphony of muscle and metal that echoed through the deepening darkness. The Roman tunnel miner's toolbox was not filled with complex machinery, but with brutally effective iron tools, each designed for a specific task in the relentless battle against the earth. The most fundamental of these was the dalibra, a versatile tool that was part pickaxe, part axe, and part hoe. Imagine a legionary or a skilled laborer swinging this all-in-one implement. One end featured a sharp pick for breaking up hard rock and prying loose stubborn stones, while the other had a flat, axe-like blade that could cut through roots, shape wooden supports, or slice into compacted soil. For many miners, the dalibra was the first and last tool they reached for, an extension of their own strength that could adapt to almost any challenge the tunnel face presented. When dealing with the hardest stone, however, a more specialized arsenal came into play. Teams of workers would employ heavy iron pickaxes to relentlessly fracture the rock, creating initial cracks and weaknesses. Then, others would step in with hammer and chisel, a timeless combination for precision work. One worker would hold a hardened iron chisel against the rock, while another struck its head with a heavy hammer. With each controlled blow, they would chip away, gradually carving out blocks or deepening grooves. This is not a process of brute force alone, but one of applied geology. Experienced miners knew to follow the natural cleavage lines in the stone, exploiting its inherent weaknesses to make their work more efficient. The constant, rhythmic clink, clink, clink of hammer on chisel would have been the defining sound of their progress, a testament to human patience and persistence. For the most monumental tasks, like quarrying large blocks or splitting massive rock formations, the Romans employed a brilliant technique known as feather and wedge. This involved drilling a series of deep holes in a line across the surface of the rock. Into each hole, they would place a pair of semi-cylindrical iron strips, the feathers, and then drive a flat, tapered iron wedge between them. Workers would then move down the line, striking each wedge in sequence, gradually increasing the tension. The simultaneous, even pressure from all the wedges would create a powerful internal force, cleanly splitting the rock along the desired line. This method allowed them to extract perfectly shaped blocks for construction with remarkable control, a clear demonstration of their understanding of physics and material science. Once the rock was broken, the debris had to be cleared. Shovels with iron blades and wooden handles were used to load the rubble into baskets or onto leather sheets. These were then dragged by hand or hauled up rudimentary ropes and pulleys to the surface, a continuous process that kept the tunnel floor clear for the next assault on the rock face. Lighting this arduous work was another challenge entirely. They relied on simple terracotta oil lamps, their flickering flames casting dancing shadows on the rough-hewn walls. These lamps consumed precious oxygen and produced thick, smoky air, adding respiratory hardship to the physical strain. Every tool, from the mighty dalibra to the humble lamp, was a piece of a larger, meticulously coordinated human machine. It was through the coordinated, relentless application of these simple iron tools, wielded by thousands of unknown hands, that the Romans slowly, inexorably, carved their will into the very bones of the earth. Yet for all the power of the dalibra and the hammer and chisel, some rock was simply too monolithic, too stubbornly solid to yield to direct force. When Roman engineers encountered a sheer mountain face or an unyielding layer of bedrock that stood directly in their intended path, they didn't retreat. Instead, they turned to one of their most audacious and dangerous methods, a dramatic application of thermal shock. This technique, often called the fire quenching method, was a spectacular display of controlled violence against the landscape. The principle was as brilliant as it was straightforward. First, laborers would build a roaring fire directly against the rock face they needed to break. They wouldn't use just any fuel. They sought out high-heat materials like dense, dry wood, or even charcoal, building a blaze so intense that the very surface of the stone would begin to glow a dull red. The heat would penetrate inches, sometimes even feet, into the rock, causing the minerals within to expand at different rates. This created immense internal stresses, a network of microscopic fractures waiting to be unleashed. Then came the critical, explosive moment. Once the rock was sufficiently superheated, crews would douse the flames with a sudden deluge of cold liquid. While water was often used, several historical accounts suggest the Romans preferred vinegar for this task. The reason is rooted in simple chemistry. Vinegar, being a weak acid, could potentially cause a more rapid and aggressive reaction with the heated minerals in the stone, particularly limestone. The thermal shock was instantaneous and violent. The outer surface of the rock, suddenly drenched in cold liquid, would contract rapidly, but the inner core of the stone, still searing hot from the fire, remained expanded. This drastic difference in temperature created opposing forces that the rock could not withstand. With a loud cracking sound, like miniature thunder from within the earth, the stone would fracture and splinter, often shearing off in large, manageable slabs. The work environment during this process was nothing short of hellish. Imagine the scene deep inside a narrow tunnel, the air thick with acrid smoke and unbearable heat, visibility reduced to near zero by the fumes. Miners, their faces covered with damp cloths, worked in a coordinated, frantic dance, stoking the fire, then scrambling back as the water or vinegar was hurled forward, the sudden steam explosion scalding the air. It was a hazardous operation with little margin for error. A misstep could mean severe burns or worse, a rockfall from an unpredictably fractured ceiling. The very act of ventilation became a life or death challenge, as the fires consumed the limited oxygen in the confined space. They likely use a system of leather bellows or even strategically placed ventilation shafts dug to the surface to create drafts, pulling the deadly smoke out and allowing just enough fresh air in for the workers to survive. This method was not used for every inch of tunnel. It was a specialized solution for the most formidable obstacles. Its primary advantage was its incredible efficiency against massively hard rock. While a team with pickaxes might take days or weeks to make significant progress through such a barrier, the fire quenching method could break apart vast quantities of stone in a single, dramatic cycle. The slabs that broke away were also often fractured along clean lines, providing useful building material rather than just useless rubble. We see evidence of this technique not only in tunnel construction, but also in their famous quarries, where the telltale signs of scorching and spalling can still be observed on some ancient rock faces. It stands as a powerful example of Roman practical science in action. They may not have understood the precise physics of thermal expansion coefficients, but they possessed a profound, empirical understanding of cause and effect. They knew that by playing fire and water against each other, they could command the stone itself to break, turning one of nature's most durable elements into a willing, if reluctant, partner in their grand subterranean ambitions. But breaking the rock and clearing the debris was only half the battle. As Roman mines and tunnels plunged deeper into the earth, they encountered a relentless, invisible enemy, groundwater. Seeping through cracks and pooling in the darkness, water threatened to flood every excavation, halting work and drowning the investment of years in a matter of days. To conquer this aquatic foe, Roman engineers deployed some of the most sophisticated machinery of the ancient world, transforming deep mining from a perilous gamble into a systematic, industrial operation. One of their most brilliant adaptations was the reverse overshot water wheel. You've likely seen images of the classic water wheel, sitting in a river, its paddles turned by the current to grind grain. The Romans, in a stroke of genius, flipped this concept entirely on its head. Deep underground, they would install a massive wooden wheel inside a dedicated shaft. But instead of the water moving the wheel, they used human or animal power to rotate the wheel itself. As it turned, a series of wooden boxes attached to its rim would dip into the flooded sump at the bottom of the mine, scoop up water, and then lift it high enough to dump it into a drainage channel carved higher up in the shaft. This created a continuous, mechanical bucket chain, capable of lifting vast quantities of water from astonishing depths, literally fighting the flood with the power of circular motion. For situations requiring water to be lifted at a steadier, more consistent flow, they turned to another Hellenistic invention that they perfected, the Archimedes screw. This device was a masterpiece of elegant simplicity. Imagine a giant wooden screw encased within a tight-fitting, waterproof wooden tube. One end of this apparatus was angled down into the mine's water pool. As laborers turned a crank attached to the top of the screw, the entire spiral blade rotated inside its tube. The magic of its design meant that with every rotation, a pocket of water would be trapped between the threads of the screw and the wall of the tube, and then gradually pushed upwards until it spilled out from the top into a waiting channel. The Archimedes screw was incredibly efficient for moderate lifting heights and could handle water thick with silt and debris, which would have jammed more delicate pumps. The rhythmic, groaning turn of these great wooden screws would have been a constant sound in the deeper Roman mines, a testament to an engineering principle so effective that it is still used in water treatment and agriculture today. Reaching those profound depths in the first place required another layer of ingenuity. Venturing hundreds of feet down was not a matter of simply digging a hole, it was an exercise in structural gymnastics. Roman miners constructed vast, intricate networks of wooden scaffolding, ladders, and platforms that turned the vertical shaft into a functional, multi-level workspace. These weren't rickety constructions, they were engineered frameworks built from sturdy timber, often braced against the shaft walls and reinforced with diagonal supports to handle the immense weight and constant vibration from the activity above and below. Ladders, sometimes just notched tree trunks, provided access for workers, while separate shafts were used for hoisting ore and waste rock to the surface using windlasses and rope. This careful zoning of traffic, separating the movement of people from the movement of material, was a critical safety innovation that prevented catastrophic accidents in the cramped, dark confines. The true scale of this endeavor becomes clear when we look at sites like the Rio Tinto mines in Spain. Here, archaeologists have found evidence of a staggering 85 such deutering wheels, arranged in pairs, cascading down a single mine shaft. This was not a piecemeal solution, it was an integrated industrial-scale pumping system. Water lifted by the first wheel would be dumped into a channel that fed the wheel just above it, and so on, in a relay race against gravity that could drain a mine to depths previously thought impossible. This systematic approach reveals a mindset that went far beyond mere excavation. The Romans were building subterranean factories, complete with their own mechanical infrastructure. They managed complex logistics, from the supply of timber for constant repairs to the organization of shift workers operating in a perpetually dark, damp, and dangerous environment. It was this combination of borrowed technology, audacious adaptation, and relentless logistical organization that allowed them to tap into the mineral wealth that powered their empire, proving that their greatest strength lay not just in the tools they wielded, but in the brilliant, systematic minds that directed their use. All this excavation, however, would have been for nothing if the tunnels couldn't hold their shape against the immense pressure of the earth. Carving out a void underground is an act of defiance against gravity itself, and the Romans knew that every tunnel, no matter how well planned, needed a strong skeleton to keep it from collapsing in on itself. Their first line of defense, especially during the initial, precarious phase of digging, was timber. As soon as a section of tunnel was cleared, specialized carpenters would move in. They didn't just prop up random logs, they constructed intricate, interlocking frames that acted as a temporary exoskeleton for the soft earth. Picture a series of sturdy wooden rectangles, each one a frame called a centering, placed one after the other like ribs along the length of the passage. These frames were often braced with diagonal supports, creating a rigid structure that bore the weight of the ceiling, allowing the miners to safely continue their work just ahead of this protective shell. This timber shoring was the tunnel's life support system, a temporary measure that absorbed the groans and shifts of the unsettled ground until a more permanent solution could be put in place. That permanent solution, the Romans' crowning achievement in subterranean architecture, was the arch. Above ground, the arch allowed for the soaring aqueducts and grand colosseums. Below ground, it was equally revolutionary. The Romans understood that an arch is an incredibly strong shape, channeling the downward force of gravity outwards to its sturdy sides or abutments. For their tunnels, they translated this principle into breathtaking underground galleries. Instead of relying on flat ceilings or simple posts, they lined the walls and roofs of their most important passages with meticulously constructed arches made of brick or stone. Teams of masons would work in the dim light, laying each brick or cut stone with precision into a curved wooden form. Once the arch was complete and the mortar, their famously durable Roman concrete, had set, the wooden form was removed, leaving behind a self-supporting vault of incredible strength. This wasn't just functional, it was beautiful. Walking through one of these tunnels, like those that served as aqueduct channels, you would be surrounded by a repeating, rhythmic pattern of perfect arches receding into the darkness, a man-made cave that felt as solid and eternal as the earth it was carved from. But what about when they encountered a section of particularly treacherous ground, loose gravel, wet sand, or soil that simply crumbled at the touch? Here, the Romans deployed a clever and counterintuitive technique known as backfilling. It sounds strange to deliberately fill in a space you just worked so hard to excavate, but their reasoning was brilliant. They would build a strong, permanent arch-lined tunnel, but instead of leaving it as an open passage, they would pack the space around and sometimes even above this new structure with a carefully selected material like loose gravel or even concrete. This backfill material acted as a buffer, evenly distributing the pressure from the unstable surrounding earth and preventing any concentrated force from bearing down on the tunnel walls. It was like building a ship within a bottle. The true, functional tunnel was the ship, strong and intact, while the backfill was the protective packing that held it securely in place against the shifting pressures of its environment. This method ensured long-term stability in the most challenging geological conditions, proving that Roman engineering was as much about working with the Earth's forces as it was about conquering them. The true testament to the success of these support systems is their longevity. Many Roman tunnels, supported by their brick arches and strategic backfilling, have remained intact and stable for 1,000 years. They have survived earthquakes, the immense weight of modern cities built above them, and the relentless seepage of water. This endurance is no accident. It is the direct result of a deep, practical understanding of physics and material science. The Romans didn't just build tunnels, they built relationships with the landscape, creating structures that negotiated a lasting peace with the forces of compression and gravity. The wooden frames provided the courage to dig deeper, the arches provided the strength to last for millennia, and the backfilling provided the wisdom to stabilize the unpredictable. Together, these methods formed the unshakable backbone of Rome's hidden world, ensuring that the empire's subterranean veins would continue to pulse long after its surface glory had faded into ruin. Even with the most powerful pumps lifting water from the depths, the Romans knew that a truly permanent tunnel required a strategy of constant, passive defense against moisture. The goal wasn't just to react to flooding, but to design the very fabric of their subterranean structures to repel water and manage its flow indefinitely. This began with an almost obsessive attention to drainage. As they excavated, they would often carve a shallow, gently sloping channel known as a cuniculus right down the center of the tunnel floor. This wasn't an afterthought, it was an integral part of the design. Any water that seeped through the walls or condensed on the ceiling would naturally find its way to this central groove. The channel would then guide this constant, slow trickle downhill, following the tunnel's overall gradient, directing it towards a designated collection point and preventing the floor from becoming a muddy, impassable quagmire. For larger, more persistent inflows, they constructed sump pits. These were essentially deep, rectangular wells dug at the lowest points of a tunnel network or at regular intervals along its length. The drainage channels would feed into these pits, which acted as underground reservoirs, collecting the water and keeping it contained below the working level of the passageway. In smaller tunnels, these sumps might simply be bailed out periodically by workers, but in more extensive systems, they became the strategic connection points for the mechanical pumps, the Archimedes screws and water wheels, which would be installed precisely here to lift the accumulated water to a higher drainage channel and ultimately out of the mine or tunnel. This combination of gravity-fed channels and strategic sumps created a multi-layered drainage system that managed everything from a steady drip to a major seep, ensuring the tunnel remained a functional, dry space for centuries. Yet the true masterpiece of Roman hydroengineering, the innovation that made all of this possible, was their revolutionary waterproof cement. Ordinary lime mortar, used by many ancient cultures, would simply dissolve when exposed to constant moisture. The Romans needed a binder that could not only withstand water, but actually cure and gain strength within it, especially for sealing aqueduct channels or building harbor structures. Their discovery of pozzolana was a paradigm shift. Pozzolana is a volcanic ash, named after the town of Pozzuoli near Mount Vesuvius, where massive deposits were found. On its own, it's just a fine, reddish-brown dust. But when mixed with lime and water, it undergoes a complex chemical reaction that creates a crystalline structure incredibly resistant to water. The process was nothing short of alchemy. Builders would combine slaked lime with the pozzolana ash, adding water to create a thick paste. When this mixture was packed into walls or used to line an aqueduct channel, something remarkable happened. Unlike regular mortar, which hardens by reacting with carbon dioxide in the air, the pozzolana mixture undergoes a pozzolanic reaction. The silica and alumina in the volcanic ash react with the lime and water to form stable, insoluble compounds like calcium silicate hydrate. This gel-like substance fills every pore and void in the mortar, creating a dense, almost stone-like mass that is virtually impermeable to water. The most astonishing quality, recorded by the architect Vitruvius himself, was that this concrete would indeed set underwater. For tunnel builders, this was a superpower. They could now line an aqueduct channel with a smooth, waterproof shell that would not leak a single drop, ensuring that the velocity and volume of the water flow remained constant over miles of its subterranean journey. The versatility of this material was astounding. They didn't just use it as a simple mortar, they engineered different concrete mixes for different challenges. For the most critical waterproofing applications, such as sealing the joints in an aqueduct or lining a cistern, they would use a mix rich in pozzolana, creating a seal as tight as any modern material. For structural elements, they would combine this pozzolana lime mortar with an aggregate of broken brick, pottery shards, or even volcanic stone, creating a concrete that was not only waterproof, but also incredibly strong and durable. This is the material that allowed them to build massive harbor walls directly in the sea, like the one at Caesarea Maritima, structures that have withstood 2 millennia of pounding waves. In the darkness of their tunnels, this same technology was at work. It meant that a drainage channel wouldn't erode, that a sump pit wouldn't leak its contents back into the surrounding soil, and that the arched vault of a critical passage would be protected from the degrading effects of moisture, ensuring the silent, dry, and enduring passage of both people and water through the very heart of the earth. Now, let's step into that world of perpetual night and consider the human experience. Imagine the profound sensory shift as a miner descended from the bright Italian sun into a narrow, winding shaft. With each step down the notched log ladder, the world above would fade, the sounds of life muffled, the warmth of the sun extinguished, until all that remained was an oppressive, absolute blackness, a silence broken only by the drip of water and the sound of your own breathing. In this environment, where a misstep could mean a fatal plunge or a tunnel collapse, light was not a mere convenience, it was synonymous with life itself. It meant the difference between striking productive rock and swinging a pickaxe into an unstable, unsupported section of ceiling. It meant being able to see the subtle crack in a timber support before it gave way. Every flicker of flame down, there was a tiny beacon of safety, a fragile circle of visibility in a world eager to reclaim its darkness. The primary tool for this battle against the gloom was the humble oil lamp or lichness. These were not complex devices. Most were simple, disposable terracotta saucers, pinched at one end to form a spout for a linen or papyrus wick. They were filled with olive oil, a fuel that was readily available throughout the empire. A worker would carry several of these lamps, their small, dancing flames providing just enough light to see the rock face immediately in front of him. But these tiny lights came with a heavy cost. They consumed precious oxygen in an already oxygen-poor environment, and their burning produced not just light, but also thick, greasy smoke laden with soot. The ceilings of Roman tunnels that were lit this way for years still bear a glossy, black patina of ancient lamp smoke, a permanent record of the thousands of hours of labor spent in that smoky haze. For the miners themselves, long exposure meant chronic respiratory problems, their lungs slowly filling with the residue of their own light source. For larger, open spaces like quarry chambers or the intersection of major tunnels, they might use torches. These provided a broader, brighter light, but they were even more voracious consumers of air and produced significantly more smoke and risk. A dropped torch in a timber-supported gallery could spell disaster, turning a life-saving tool into an instrument of instant inferno. The management of this risk reveals another layer of their planning. They understood ventilation not as an abstract concept, but as a tangible engineering challenge. To combat the buildup of foul air, which they knew could extinguish lamps and cause dizziness or death, they engineered a passive ventilation system using vertical shaft. While a tunnel was being dug, crews would periodically sink a narrow shaft from the tunnel, sealing up to the surface. These light wells served a dual purpose. Primarily, they acted as chimneys, creating a draft that pulled the stale, smoky, oxygen-depleted air out of the tunnel and drew fresher air in from the main entrance or other shaft. This natural convection was a lifesaver, constantly replenishing the atmosphere and making prolonged work deep underground possible. The secondary, brilliant function of these shafts was to harness the sun itself. During the day, a vertical shaft would funnel a narrow beam of direct sunlight down into the Stygian darkness, illuminating a specific spot on the tunnel floor with startling clarity. While this didn't light the entire passage, it created vital pools of pure, clean light at key workstations or intersections. Some historians suggest they may have amplified this effect by using polished metal shields or sheets of mica placed at the surface to better reflect and direct the sunlight downward. This practice of carving these lucernaria, or light holes, demonstrates a sophisticated understanding of their environment. They weren't just fighting the darkness with fire, they were recruiting the power of the world above, piercing the earth with needles of light to assist their monumental task. This constant three-front battle against rock, against water, and against darkness forged a unique type of worker. These were not just laborers, they were specialists in subterranean survival, their senses attuned to the subtle warnings of their environment. The behavior of their lamp flames was a critical gauge. A flame that burned low and blue signaled a dangerous buildup of toxic gases or a lack of oxygen, a silent alarm to evacuate immediately. A flickering that was out of rhythm with their movement could indicate a draft from a hidden fissure, perhaps one leading to a hidden water source or an unstable cavity. In the absolute quiet, they learned to listen to the sounds of the mountain, the creak of timber supports under stress, the ominous trickle of loose soil, the distant rumble that presaged a collapse. Their work was a dialogue with the earth, conducted in a language of flame, sound, and touch, a testament to human adaptability in the most hostile of environments, where every glimmer of light was a hard-won victory in the endless night. Yet for all the brilliance of their engineering and the power of their tools, none of these subterranean marvels would exist without the immense human engine that drove them into reality. The true cost of Rome's underground ambition was paid not in gold, but in the sweat, blood, and foreshortened lives of the countless individuals who transformed blueprints into tunnels. This workforce was a meticulously stratified society in miniature, a stark reflection of the empire itself, where a tiny elite of minds directed the labor of a massive, expendable underclass. At the very top were the architecti, the master engineers and architects. These were highly educated, literate men, often from respectable families, who possessed a formidable knowledge of geometry, physics, and hydraulics. They were the visionaries who surveyed the routes, designed the support arches, and calculated the precise gradients for aqueducts. A project's success or failure rested on their expertise, and their reputations were built on the stability of the structures they conceived. Working alongside them were the librators, the surveyors who operated the gromas and chorobates, translating theoretical lines on parchment into physical markers on the landscape. These were the practical technicians, the bridge between the drawing board and the digging face, ensuring that the grand vision was executed with pinpoint accuracy. But the actual work of moving the earth fell to a different class of laborer entirely. Directing the day-to-day operations were overseers and foremen, often army veterans or freedmen known for their discipline and organizational skills. They managed the logistics, distributing tools, setting work quotas, and maintaining a brutal pace of progress. Beneath them were the skilled free workers, carpenters who built the intricate timber supports, masons who laid the perfect brick arches, and blacksmiths who tirelessly sharpened and repaired the endless stream of broken iron tools. These men commanded higher wages and a degree of respect, their specialized crafts making them indispensable to the operation. They worked in the same dangerous conditions as everyone else, but their expertise offered a sliver of security and slightly better treatment. It was beneath this layer, however, that we find the true backbone and tragedy of Roman tunneling, the legion of unskilled laborers who provided the raw, brute force. This group was a grim tapestry of the empires oppressed and conquered. Vast numbers were slaves, captured in Rome's endless wars of expansion from Gaul, Thrace, Britain, and beyond. They were property bought and sold like livestock, and their lives were considered a cheap and renewable resource. Alongside them toiled prisoners of war who faced a sentence of hard labor as an alternative to execution. Perhaps the most desperate group were the damnati in metallum, condemned criminals sentenced to the mines. For these men, a tunnel was not a workplace. It was a subterranean prison from which there was no escape, a death sentence carried out in slow, grueling installments. Their lives were brutally short. The historian Diodorus Siculus, describing the gold mines of Egypt under Roman control, painted a horrifying picture. He wrote that the workers, including old men and children, labored without respite day and night, naked and in chains under the whips of overseers. The air was filled with dust and the constant threat of tunnel collapse, and there was no one to hear their cries or lamentations. While conditions may have varied, this account captures the essential horror faced by those at the very bottom of this human hierarchy. The physical toll was unimaginable by modern standards. The constant swinging of heavy picks and hammers led to crippling joint injuries and spinal deformities. Lungs were ravaged not just by the smoke from oil lamps, but by the fine, sharp dust from cutting sandstone and quartzite, leading to a form of silicosis that slowly suffocated its victims. The noise in a confined tunnel, with multiple teams hammering and chiseling simultaneously, must have been deafening, leading to widespread hearing loss. The darkness, broken only by feeble lamplight, ruined their eyesight. Malnutrition and dysentery were rampant, as their meager rations were often insufficient to fuel such intense physical exertion. For the slaves and the condemned, medical care was non-existent. An injury that prevented work was often a death sentence. They lived and died in a world of perpetual shadow, their bodies broken to feed the insatiable appetite of an empire that glorified the marble and gold above, while willfully ignoring the human cost extracted from the darkness below. This stark division between the minds who designed and the hands who built is the untold story of Roman engineering, a testament to human ingenuity, yes, but also a sobering reminder of the profound human suffering upon which so much ancient grandeur was founded. Nowhere was this marriage of ambition and precision more perfectly expressed than in the aqueduct system, and in particular, the long, hidden tunnel sections that formed its vital arteries. While we picture soaring stone arcades marching across valleys, the reality is that up to 80% of a typical Roman aqueduct's length was actually a subterranean channel, carefully carved through hills and buried just beneath the surface of farmland. This was a deliberate choice. Tunneling avoided the immense cost and complexity of building endless bridges, but more importantly, it protected the water supply from contamination, evaporation, and even potential enemy attack. The true engineering challenge, however, was not the digging itself, but maintaining an almost impossibly gentle and unwavering slope for dozens, sometimes hundreds, of miles. The water flowing from a distant spring had to arrive in the city with just the right amount of force. Too steep a gradient and the water would rush through, eroding the channel walls; too flat, and it would stagnate, becoming a sluggish, algae-filled trickle. The target was a slope of just a few inches per 100 feet, a gradient so slight it's barely perceptible to the human eye, yet it had to be maintained with unerring accuracy across an entire landscape of hills, valleys, and uneven terrain. To achieve this, Roman surveyors performed what can only be described as a topographic ballet. Using their chorobates, they would establish a series of level lines across the countryside, creating a continuous elevation profile from the water source all the way to the city. If a hill stood in the way, they had two choices. They could go over it by building a raised covered channel, which was expensive, or they could go straight through it with a tunnel, which required staggering confidence in their measurements. The decision to tunnel through a mountain was a monumental commitment. Crews would begin digging from both sides, and the terror for every engineer was the possibility that the two teams would fail to meet in the middle, resulting in a costly and humiliating misalignment. To prevent this, the surveyors established a series of vertical shafts, known as puttae, sunk from the surface down to the planned level of the tunnel at regular intervals along its route. These shafts were not just for ventilation or lifting rubble, they were the project's navigational lifeline. As the tunnel advanced from the bottom of each shaft, surveyors could constantly verify their direction and, most critically, their depth, ensuring they were maintaining that crucial gradient. The teams digging from opposite ends of the mountain were, in effect, always digging toward these known intermediate points, dramatically reducing the margin for error. The remains of these shafts, visible as lines of circular holes dotting the landscape above ancient aqueduct routes, are the silent footprints of this meticulous process. Once the tunnel was hollowed out, the final act was to create a perfect conduit for the water. The rough-hewn rock channel was transformed by lining it with the Roman signature waterproof concrete, a mix of lime and the miraculous pozzolana ash. This created a smooth, slick, and impermeable shell that minimized friction and prevented any precious water from seeping out into the surrounding earth. The result was a man-made river, flowing silently and reliably through the dark, its level and speed dictated by an unchangeable law of gravity and a gradient set in stone centuries before. This hidden, subterranean delivery system was the real genius of the Roman water network. It allowed a city like Rome to eventually be supplied by 11 major aqueducts, delivering over 1 million cubic meters of fresh water every single day. That water flowed continuously to public fountains, lavish bathhouses, and even private homes, enabling a level of urban sanitation and public health that would not be rivaled in Europe for over 1,000 years. The aqueduct tunnel, therefore, stands as the ultimate expression of Roman utilitarian philosophy, a masterpiece of engineering hidden from view, its grandeur not in its appearance, but in its flawless, life-sustaining function. While the aqueducts channeled the lifeblood of water, another type of tunnel pumped the financial lifeblood directly into the empire's heart, the mines. To grasp the sheer scale of Roman ambition, you have to look beyond the city walls to places like Las Medulas in Spain. What you see today is a breathtaking, almost alien landscape of jagged red peaks and deep, serene lakes. But this wasn't carved by nature alone. It is the scar left by the most aggressive mining operation the ancient world had ever seen. Here, the Romans weren't just digging discrete tunnels, they were re-engineering entire mountains to get at the gold within, and their method of choice was a spectacular and destructive technique known as ruina montium, the wrecking of mountains. This process began not underground, but with an immense hydrological network built high in the surrounding hills. Engineers would construct massive reservoirs to capture seasonal rainwater and snowmelt. When a reservoir was full, they would open a sluice gate, releasing a colossal, directed wave of water down a specially constructed channel. This torrent would then hit a complex network of smaller channels and tunnels that had been dug throughout the mountain, often by slave labor. The sudden, immense pressure of the water exploding through these internal passages would literally blast the mountain apart from the inside out. The resulting landslide of fractured rock and soil would then be sluiced through a series of channels where the heavier gold particles would settle out, trapped by wooden riffles or bundles of thorny brush. This was mining on an industrial, almost geological scale, a deliberate and calculated act of environmental transformation to fuel the imperial treasury. For deposits that were less accessible to such surface assaults, or for following precious veins of copper and silver deep into a mountainside, the Romans employed a more targeted hydraulic method called hushing. This was like ruina montium on a more precise, repeatable scale. Rather than trying to collapse a whole mountain, miners would use water as a giant, powerful scalpel. They would build a large tank or dam above a suspected mineral vein. Once filled, the water was released in a controlled but powerful surge that would tear away the topsoil and weathered rock, effectively stripping the hillside bare and exposing the solid bedrock beneath. By repeatedly husking an area, they could reveal the colorful, telltale stains of oxidation that marked an ore vein running through the rock. It was an incredibly efficient form of prospecting and initial excavation, using the power of gravity and water to do the work of thousands of men with picks and shovels. Once the valuable vein was laid bare, the real tunneling could begin. Miners would then follow the snaking path of the ore deep into the mountain, creating the intricate honeycombed networks we see at places like Montana in Romania. These weren't simple holes. They were sophisticated underground quarries, with tunnels carefully cut to extract the maximum amount of ore while leaving just enough rock in place to prevent the entire structure from collapsing in on itself. Inside these mines, the extraction of ore was a dark, dangerous, and methodical process. Once a rich vein was identified, often gleaming with the distinctive green of copper or the brassy yellow of gold-bearing rock, teams of miners would set to work with their iron tools. They used their picks and wedges not to create large, open spaces, but to carefully fracture the ore along its natural cleavage lines. The precious rock was then loaded into leather bags or baskets and passed hand over hand along a human chain out of the narrow, cramped tunnels. In larger mines, donkeys might be used to haul the ore to the surface, but the initial work was almost always done by human muscle in near total darkness. The air would have been thick with rock dust and the smell of sweat and smoke from the oil lamps. The constant danger of collapse was ever present, and the timber supports that held up the ceilings would groan under the weight of the mountain above. These miners, many of them slaves or condemned criminals, were working in a hellish environment, their short lives dedicated to prying the wealth from the stone that would mint the coins, craft the statues, and gild the palaces of an empire that most of them would never see. The logistical challenge of processing all this rock once it reached the surface was another monumental task. The ore coming out of the tunnels was just that rock containing tiny amounts of precious metal. To extract the gold or silver, it first had to be crushed. This was often done using massive stone mills, powered by water wheels or animal labor, that would grind the rock into a fine powder. This powder was then washed over gentle slopes or through shallow channels. Because gold and silver are significantly heavier than the surrounding rock, they would settle out while the lighter waste material, known as gangue, was washed away. For copper and other base metals, a smelting process was required. The crushed ore would be mixed with a flux like limestone and heated in a furnace to incredibly high temperatures. This would separate the pure metal, which would melt and run to the bottom of the furnace, from the useless slag, which should be skimmed off the top. The scale of this waste is almost unimaginable. At Las Magelas, it's estimated that the Romans moved over 300 million cubic feet of earth and rock to produce just 5 million pounds of gold. This means they were processing staggering volumes of material for a shockingly small yield, a testament to the immense value they placed on these metals and the seemingly limitless labor force they had at their disposal. This relentless extraction had a dual legacy. On one hand, The gold from Las Medulas and the silver from mines in Spain and the Balkans funded the Roman state for centuries. It paid the legions that guarded the frontiers, it built the infrastructure that connected the empire, and it created the luxurious lifestyle for the elite in Rome. The very stability and expansion of the empire was underwritten by the metal ripped from these tunnels. Yet the other legacy is one of profound human and environmental cost. The landscape at Las Medulas is beautiful today, but it is a monument to destruction. The hushing and ruina montium techniques caused massive erosion and silted up rivers for miles downstream. And as we've seen, the human cost was astronomical, with countless lives spent in the dark, toxic confines of the mines. The Roman mining tunnel, therefore, stands as a powerful symbol of the empire's core paradox. It was a civilization capable of breathtaking engineering and systematic organization, but it was built upon a foundation of relentless resource extraction and human suffering, where the glitter of gold above ground was forever shadowed by the darkness of the tunnels from which it came. While the vast mining and aqueduct tunnels served the practical needs of empire, the Romans also carved out subterranean spaces for a life of luxury, privacy, and political intrigue, most famously in the form of the cryptoporticus. This was not a dark, cramped mine shaft, but rather a sophisticated semi-subterranean gallery, a long, covered passageway that was partially buried, with a series of arched openings along one side that let in filtered light and air while keeping the interior cool and shadowy. Think of it as an ancient precursor to the modern air-conditioned corridor. In the scorching heat of a Mediterranean summer, the cryptoporticus provided a perfectly temperate environment for a leisurely stroll, completely protected from the relentless sun. For the wealthy Roman aristocrat, this architectural feature was the ultimate symbol of refined living, transforming a simple need for coolness into an experience of opulent comfort. But the cryptoporticus had a far more intriguing second life, one that speaks directly to the clandestine nature of Roman high society. Its design made it the perfect vehicle for discretion. Because it was partially sunk into the ground, it often ran beneath the main courtyards and gardens of lavish villas and imperial palaces, connecting different wings of the complex without requiring a person to step into the open. This allowed the elite emperors, senators, and powerful freedmen to move about their own homes completely unseen by guest staff or even family members. In the volatile world of Roman politics, where alliances shifted like sand and a public appearance could be misinterpreted, the ability to move in secret was a powerful asset. A senator could slip away from a boisterous dinner party in the triclinium, descend into the cool, echoing silence of the cryptoporticus, and emerge moments later into a private study to meet with a confidential informant, all without anyone in the main house being the wiser. Some of the most stunning examples survive in the buried cities of Pompeii and Herculaneum. At the Villa of the Papyri in Herculaneum, a magnificent cryptoporticus stretches for 250 meters, its walls once adorned with beautiful frescoes. Walking through it today, you can still feel its dual nature. On one hand, a serene, art-filled promenade offering lovely framed views of the seaside garden. On the other, a profoundly isolated and secretive thoroughfare. In Rome itself, the Palatine Hill, the epicenter of imperial power, is honeycombed with these hidden passages. The cryptoporticus beneath the Palace of Domitian, for instance, is a sprawling, labyrinthine network. Historians strongly suspect this very passage was used by the Praetorian Guard to covertly move through the palace, and it was likely the route used by the assassins who murdered the infamous Emperor Caligula, allowing them to approach their target without raising alarm. In this context, the cryptoporticus was more than a luxury. It was a tool for survival and conspiracy. Its shaded arches witnessing whispers of plots that could change the course of history. This architectural innovation perfectly encapsulates a fundamental duality in the Roman character. Publicly, they celebrated light, openness, and civic virtue in their forums and temples. But privately, they cultivated shadow, secrecy, and the manipulation of perception. The cryptoporticus was the physical manifestation of this double life. It provided a controlled environment where the social performance of the upper class could be paused. where the toga-clad public figure could momentarily vanish and become a private, scheming individual. It was a space that balanced the practical need for comfort with the psychological need for concealment, proving that for the Roman elite, the most important journeys often happened not under the sun, but just beneath it, in the elegant, echoing twilight of their hidden world. Of all the hidden veins running beneath Rome, perhaps none was more vital or more viscerally symbolic than the Cloaca Maxima, the Great Sewer. Its story begins not with grand arches and imperial decrees, but with a swamp. In the earliest days of the city, the valley that would become the Roman Forum was a poorly drained marshland, a breeding ground for disease, and a literal obstacle to the city's growth. In the 6th century BCE, under the rule of the Etruscan kings, a monumental decision was made to channel these pestilential waters away. The initial project was audacious in its simplicity. They carved out a massive, open-air ditch, directing the flow of several streams through the Forum and out toward the Tiber River. This is not yet the enclosed tunnel we imagine. It was a raw, open wound in the landscape, a utilitarian solution to a fundamental problem of urban survival. Yet, this humble beginning would become the foundation for one of the ancient world's most enduring public works. Over the centuries, as Rome grew from a regional power into a sprawling metropolis, the open channel became an unacceptable blight in the heart of its civic center. The transformation began in the 3rd century BCE, as Roman engineering confidence surged. They embarked on the Herculean task of enclosing the vast ditch, building a monumental vaulted tunnel right over and around it. Imagine the scale of this operation: crews working to divert the water temporarily, while teams of masons constructed a ceiling of massive stone blocks, creating a subterranean canyon wide enough for a small boat to navigate. This was no mere pipe, it was an underground river, a man-made cavern dedicated to carrying away the city's waste and stormwater. The Cloaca Maxima became the main artery of an expanding subterranean circulatory system, with smaller public and private drains from across the city feeding into it, all flowing by gravity down to its mouth, which still empties into the Tiber near the Ponte Rado Bridge. The engineering behind its longevity is as impressive as its scale. The tunnel was built with a consistent, gentle gradient, ensuring a self-cleansing flow that prevented blockages and stagnation. Its walls were lined with the Roman signature waterproof cement, and the sheer volume of the structure, large enough in parts for a person to stand upright inside, meant that even during heavy rains, it could handle a tremendous surge without backing up into the streets above. Maintenance was a perpetual and perilous civic duty. Historical records tell us that the aediles, the magistrates responsible for public works, would organize cleaning crews to venture into the depths. These men would navigate the dark, fetid passages, likely by boat or on wooden walkways, to clear debris and silt that accumulated over time. It was a foul and dangerous job, but it was essential. The health of the entire city literally flowed through this channel. Beyond its practical function, the Cloaca Maxima held a profound symbolic power for the Romans. They saw it not as a shameful secret to be hidden, but as a triumphant symbol of their mastery over nature. The writer Pliny the Elder captured this sentiment perfectly, marveling that the sewers, vaulted with stone and wide enough for wagons loaded with hay to pass through, were among the most astounding achievements of Rome. To them, this underground river represented order conquering chaos, civilization taming the wild, disease-ridden swamp upon which their city was founded. It was a tangible reminder that Roman greatness was built not just on military conquest and law, but on the unglamorous, essential work of public health and urban infrastructure. The fact that it functioned effectively for over 1,000 years is a testament to the soundness of its original design and the Roman commitment to maintaining the systems that sustain their way of life. In the end, the Cloaca Maxima was more than a sewer. It was a declaration that even the most fundamental, unpleasant aspects of city life could be engineered into a monument of enduring strength. Yet even as the Cloaca Maxima channeled away the physical impurities of the city, another vast network of tunnels was being carved into the soft rock beyond its walls, addressing a different, deeply human need: the quest for a dignified rest in the afterlife, and a space for faith to flourish under persecution. Far from the bustling heart of Rome, along the quiet consular roads that radiated out into the countryside, early Christians and Jewish communities began creating an astonishing subterranean world known as the catacomb. These were not tunnels for water or warfare, but for the dead, and they would become one of the most poignant and extensive uses of underground space in the entire Roman world. The primary reason for going underground was simple and practical. Roman law strictly forbade burial within the sacred boundary of the city itself. For a growing and often marginalized Christian community, purchasing small plots of land above ground for individual graves was financially impossible. The catacombs provided an egalitarian and space-efficient solution. By digging down, they could create thousands of burial spaces in a relatively small surface area, ensuring that every member of their community, rich or poor, could be laid to rest according to their customs. The geology of the Roman countryside was perfectly suited for this purpose. Just beneath the topsoil lay thick strata of tufa, a soft, granular volcanic rock. This wasn't the hard, monolithic stone that required fire and vinegar to fracture. Tufa could be easily excavated with simple picks and shovels. Its key characteristic was that it was firm enough to hold its shape when first cut, yet soft enough to be worked with basic tools. This allowed teams of specialized diggers, known as fossors, to carve out incredibly precise and stable galleries without the need for complex arches or timber support. The fossors were the unsung engineers of this funerary world. They worked in organized guilds, and their entire profession was dedicated to this singular, sacred task. They would begin by sinking a rectangular shaft, known as a lucernarium, down from the surface to a depth of perhaps 20 or 30 feet. This shaft served as the primary access point, providing not only a way for workers and mourners to descend via ladders, but also light and ventilation for the galleries they would soon branch out from its base. From the bottom of this main shaft, the fossors would begin their meticulous work, carving long, narrow corridors just wide enough for two people to pass. The walls of these corridors were then transformed into a honeycomb of burial niches, known as loculi. These were horizontal recesses, each one just large enough to hold a single body, which would be wrapped in a linen shroud and sometimes placed in a simple terracotta or marble sarcophagus. The opening of the loculus would then be sealed with a slab of marble or terracotta tiles, which were often inscribed with the name of the deceased, a simple prayer, or symbolic carvings like a fish or an anchor. These sealed fronts created a smooth, almost monolithic wall on either side of the corridor, a sober and orderly landscape of remembrance. The loculi were stacked vertically from floor to ceiling, sometimes reaching 10 or 12 tiers high. To access the highest niches, the fossors would carve small footholds directly into the tufa walls, a testament to the practical considerations that governed every aspect of this underground city of the dead. As a community grew and more burial space was needed, the network would expand in a remarkably systematic way. New galleries were dug parallel to the original ones, connected by shorter cross passages, creating a vast grid-like labyrinth on multiple levels. Staircases and additional light wells connected these different floors, creating a true multi-story complex beneath the earth. Some of the largest catacombs, like those of St. Calixtus, eventually stretched for over 12 miles and descended 4 or 5 levels deep, containing the remains of 500,000 individuals. Despite their immense scale, these were not chaotic warrens. The fossors maintained meticulous planning, ensuring the stability of the entire structure by leaving sturdy pillars of untouched tufa at regular intervals to support the ceilings. Walking through these silent, dark galleries today, one is struck by the order and the profound sense of community. The narrow passages, lined floor to ceiling with the sealed tombs of generations, feel less like a place of horror and more like a densely populated neighborhood, a city within a city where social distinctions were erased in the shared equality of death. But the catacombs were far more than just an underground cemetery. During periods of intense persecution, particularly in the 3rd century, these subterranean networks took on a second, vital life as clandestine places of refuge and worship for the early Christian community. While it's a popular myth that Christians lived in the catacombs to hide from authorities, the reality is more nuanced. They were first and foremost cemeteries, and Roman law generally respected burial sites as sacred and inviolable. This legal protection made them relatively safe spaces for a persecuted group to gather. On the anniversaries of a martyr's death, families and fellow believers would descend into the catacombs to hold a funerary meal or refrigerium near the tomb. These gatherings, held in small vaulted rooms called cubicula that were often decorated with frescoes, would naturally evolve into prayer services and the celebration of the Eucharist. It is in these small, intimate cubicula that we find the earliest surviving Christian art. The walls and ceilings are adorned with frescoes that blend classical Roman imagery with new Christian symbolism. You see depictions of the Good Shepherd, a figure carrying a lamb on his shoulders that resonated with both Christian and pagan viewers. Scenes of Jonah and the whale symbolized resurrection and salvation, while orants, figures with arms raised in prayer, represented the faithful soul. They also painted fish, an acronym for Jesus Christ, Son of God, Savior in Greek, and anchors, a symbol of hope. This art was not merely decorative, it was a visual theology, a source of comfort and instruction for a community that could not worship openly. The atmosphere in these chambers, lit by the flickering light of oil lamps, would have been profoundly moving, a small congregation huddled in a tomb, surrounded by images of their faith, finding strength and hope in the very place they laid their dead to rest. The catacombs, therefore, represent a unique fusion of the practical and the spiritual. They solved a pressing logistical problem with brilliant, simple engineering in the soft tufa rock, while simultaneously providing a hidden sanctuary where a vulnerable faith could nurture its identity, develop its art, and ultimately gather the strength to survive and one day transform the empire itself. This hidden world of tunnels wasn't just for water, burial, or luxury. It also became a brutal, terrifying theater of war. When a Roman army laid siege to a well-defended city, the confrontation wasn't only happening on the surface, with battering rams assaulting gates and arrows flying over ramparts. A parallel, invisible war was being waged deep underground, in a claustrophobic battle of wits and willpower fought in near-total darkness. The Roman military mind was one of the most psychologically devastating weapons in their arsenal. The goal was audacious, to literally undermine the enemy's greatest strength, their walls. Legionaries, many of whom were trained as combat engineers, would begin digging a tunnel from the safety of their own lines, far from enemy archers. This was no simple hole. It was a carefully engineered subterranean corridor, shored up with timber just like a mine, designed to travel silently beneath the killing ground between the armies and emerge directly underneath the foundations of a key tower or section of the city wall. The process was a masterpiece of military precision and patience. The entrance to the mine, known as the gallery, would be concealed within the Roman siege works. Teams of soldiers, working in shifts around the clock, would excavate the tunnel using the same dolobres and baskets they used for civilian construction. The excavated earth was a constant problem. It had to be discreetly disposed of to avoid alerting the defenders to their activity. They would often mix this fresh soil with the material from their own defensive ramparts or scatter it in nearby streams under the cover of night. As the tunnel advanced, sometimes for hundreds of feet, carpenters followed close behind, installing the wooden frames that kept the soft, unstable earth from collapsing on the diggers. The air grew thick and foul, lit only by the faint, smoky glow of oil lamps, and the only sounds were the muffled thud of tools, the shuffling of feet, and the labored breathing of men working in an increasingly oxygen-poor environment. Once the tunnel reached its target, the final, dramatic phase began. The miners wouldn't just dig an open space. They would carefully hollow out a large chamber directly beneath the wall's foundation, again using timber to prop up the ceiling. This chamber was the bomb. When it was ready, the Romans would pack it with highly combustible material, dry brushwood, straw, and oily rags. Then the moment of truth arrived. They would set the fuel ablaze and make a frantic retreat. The fire would rapidly consume the wooden support pillars holding up the chamber's roof. As those timbers turned to ash, the ceiling of the chamber, which was the very ground supporting the wall above, would suddenly have nothing holding it up. The earth would give way, and with a thunderous roar, a massive section of the enemy's fortification would crack, tilt, and come crashing down into a heap of rubble, creating a breach for the Roman infantry to storm. But the defenders were not passive victims. They developed sophisticated counter-tactics, turning the Romans' own weapon against them. The most common defense was a practice called countermining. Suspicious defenders would place their ears against the ground inside the city or dig listening pits, where soldiers with keen hearing could detect the faint, telltale sounds of digging, the scrape of a shovel, the tap of a pickaxe echoing through the soil. Once they pinpointed the direction of the enemy mine, they would launch their most terrifying response. They would dig their own tunnel to intercept it. This set the stage for a subterranean battle, a brutal close-quarters fight in a space so cramped that men could barely swing a sword. These encounters in the pitch-black galleries were pure chaos and horror. Soldiers would clash in the narrow confines, using short swords, daggers, and spears in the choking dust and smoke, each side struggling for control of the underground passage. The goal for the defenders was to break into the Roman mine, kill the sappers, and collapse the tunnel before it could reach its target. Sometimes, the defenders would use more ingenious and horrifying methods than simple steel. If they located the Roman gallery, they might not even engage in direct combat. Instead, they would dig a small opening into the enemy tunnel from above or the side and then pour in noxious substances. They would fill braziers with feathers and set them smoldering, pumping the thick, acrid smoke into the Roman mine to suffocate the soldiers inside. There are even accounts of defenders releasing swarms of agitated bees or wasps into the tunnels, or flooding them by diverting a city's water channel, drowning the attackers in the dark. These underground battles were a unique form of psychological warfare. For the soldiers on the surface, the real fear wasn't the visible enemy, but the unseen one below. The ground beneath their feet, which should have been solid and secure, was now a potential death trap. The constant gnawing anxiety that the earth could literally open up and swallow them at any moment, or that enemy soldiers could emerge from a hidden hole inside their own city, shattered morale and created an atmosphere of pervasive dread. The Roman siege mine, therefore, was more than an engineering tool. It was a weapon that attacked the enemy's mind as much as their walls, proving that in ancient warfare, the most decisive blows could come from the most unexpected direction, from the silent, shifting darkness beneath the battlefield. Now, let's pull back another layer of this hidden world and journey directly beneath one of Rome's most magnificent public spaces, the immense baths of Caracalla. On the surface, this was a paradise of light and leisure. Citizens would stroll through sun-drenched courtyards adorned with priceless sculptures, exercise in vast open-air palestras, and then move inside to a sequence of grand halls, the cool frigidarium, the warm tepidarium, and the steamy domed calidarium. The air was perfumed with scented oils, the sounds were of conversation and splashing water, and the entire experience was designed to awe and relax. But this vision of serene opulence was an illusion made possible by a frantic, invisible city of industry operating just below the marble floors. While bathers lounged and socialized, an entire subterranean workforce toiled in a parallel universe of narrow passageways, roaring furnaces, and complex plumbing, ensuring that the perfect temperature, clean water, and pristine environment above were maintained without a single moment of interruption. The sheer scale of the logistics required to run these baths is almost incomprehensible. The baths of Caracalla could accommodate over 1,600 bathers at a time, and keeping the hot rooms heated and the pools filled required a hidden infrastructure as sophisticated as the visible one. The entire complex was raised on a series of massive brick piers, creating a cavernous underground world known as the Hypocaust Foundation. This wasn't just a crawl space, it was a multi-story subterranean factory. The most critical element down there was the army of slaves who served as the human engine of the baths. Dozens of them, perhaps even hundreds, were constantly on the move through a network of service tunnels, their world defined by heat, noise, and relentless labor. Their primary back-breaking task was fuel management. The hypocaust system, which heated the floors and walls, required a constant, enormous supply of wood. Great furnaces, or prefurnia, burned day and night, and slaves had to ferry a continuous stream of firewood from underground storage yards to these roaring mouths of heat. They moved like a disciplined ant colony along designated routes, ensuring that the patrons above never saw a soot-covered laborer or heard the rumble of a fuel cart. Water management was another monumental challenge orchestrated entirely from below. The baths consumed millions of gallons of water daily, flowing in from a dedicated aqueduct branch. But this water wasn't just dumped into the pools. Beneath the main bathing halls, a labyrinth of lead and terracotta pipes snaked through the darkness, all controlled by a series of sluice gates and valves. Specialized slaves, who were essentially underground plumbers, constantly monitored and adjusted this flow. They had to ensure that the frigidarium's pool remained cold and refreshing, while the massive bronze boilers in the service areas delivered scalding water to the calidarium. The used water, in turn, had to be efficiently drained away through another set of tunnels that fed into the main city sewers. This constant cycle of supply, distribution, and drainage was a ballet of hydraulic engineering, all managed from the dark, humid corridors beneath the bathers' feet. Maintenance and repair in this environment were perpetual and had to be completely invisible. If a pipe sprang a leak or a floor mosaic above needed fixing, the work could not disrupt the daily routines of thousands of patrons. The underground tunnels provided the perfect solution. A maintenance crew could access any point in the complex from below. They could shore up a foundation, replace a section of lead piping, or even ascend through hidden staircases and trapdoors into service closets that opened directly into the grand halls, all while remaining unseen. This separation of patron and laborer was a deliberate design principle, a stark physical manifestation of the Roman social order. The world above was for odium or leisure, a realm of light, beauty, and social display. The world below was for negodium, business, and work, a realm of darkness, utility, and anonymity. The breathtaking experience of the Roman baths was thus a carefully crafted illusion, a spectacle made possible only by the existence of this mirror image city of toil, where the comfort of the privileged was directly purchased with the silent, strenuous labor of the unseen. While the legions of miners were chasing veins of precious metal deep underground, another equally vital tunneling operation was underway in the open-air quarries that dotted the empire. Here, the goal was not to follow a narrow seam of ore, but to extract massive, perfectly shaped blocks of stone, the very building blocks of Rome's iconic architecture. The magnificent travertine for the Colosseum, the creamy Carrara marble for the Pantheon's columns, and the durable tuff for countless temples and walls all began their journey in these vast terraced excavations. But getting these colossal stones out of the living rock in usable forms required a method just as ingenious as the fire quenching technique, but one that relied on a quieter, more patient kind of force. The primary challenge was control. How could you split a mountainside along a precise, straight line without shattering the entire block into useless rubble? The Romans solved this with an elegantly simple application of physics, using the power of expansion to do the work of a giant's hammer. The process began with the same specialized tools that echoed in the mines, the hammer and chisel. However, in the quarry, their use was one of meticulous precision rather than brute force. Teams of quarrymen, armed with heavy iron-pointed chisels, would first clean and smooth the surface of the rock face, identifying the natural grain or cleavage plane along which the stone would most easily split. Once they had determined the line for their block, they would begin the laborious task of drilling. Using a hammer and a handheld chisel, or sometimes a heavier chisel struck by a team, they would create a series of deep, closely spaced holes along the intended fracture line. The spacing was critical, too far apart, and the rock would fracture unevenly, too close, and it was wasted effort. These holes weren't random. For a block intended to be a massive column shaft, they might drill a straight line to split a slab from the cliff. For rectangular building blocks, they would drill holes along two perpendicular sides to define the block's dimensions before undercutting it from beneath. The rhythmic tap-tapping of countless hammers was the soundtrack of the quarry, a persistent, patient percussion that slowly prepared the stone for its transformation. Once the line of holes was drilled, the quarrymen would insert their secret weapons, a pair of semi-cylindrical iron strips known as feathers, and a flat, tapered iron wedge. The feathers were placed into the hole first, facing each other to form a cylindrical lining. Then, the wedge was carefully driven between them. This assembly was repeated in every hole along the fracture line. Now came the moment of controlled tension. The workers would move systematically along the line, striking each wedge in sequence with heavy sledgehammers. They wouldn't drive any single wedge all the way in at first. Instead, they would tap each one just a little, then move to the next and the next, going back and forth along the line. This ensured the tension built evenly across the entire face of the stone. With each pass, the wedges were driven deeper, the iron feathers transmitting the immense outward pressure directly against the walls of the drilled holes. The stone, under this steadily increasing, distributed strain, would begin to groan. Then, with a sharp, loud crack that echoed across the quarry, it would surrender, splitting cleanly along the precise line defined by the holes. It was a triumph of applied force, turning the inherent brittleness of the stone from a liability into a tool. But for certain types of rock, particularly in regions where metal was scarce, or for softer stones like limestone, the Romans employed an even more subtle and brilliant variation of this technique, one that traded the ring of iron for the silent, inexorable power of water. Instead of iron feathers and wedges, quarrymen would carve a series of deep, rectangular slots into the rock face. Into these slots, they would drive dry, seasoned wooden wedges made from a hard, dense wood like oak. Once the wooden wedges were firmly seated in their slots, the crew would thoroughly soak them with water. Wood, of course, expands as it absorbs moisture. Trapped within the unyielding confines of the stone slot, the wedges had nowhere to go. As they swelled, they generated a tremendous, continuous, and silent outward pressure, far more gradual and uniform than the impact of a hammer. Over hours, this relentless, slow-motion force would build until, just like with the iron wedges, the rock would fracture along the desired plane. This hydroexpansion method was incredibly effective for producing very fine, smooth splits, minimizing the risk of hidden microfractures that could weaken a block destined for a critical structural. It was a patient man's game, a testament to the Roman understanding that not all power needs to be violent or immediate sometimes. The most reliable force is the one that works slowly, quietly, and inevitably. The final step, once a massive block was successfully split from the mother rock, was to free it from its bed and prepare it for transport. This often involved a technique called undercutting. Quarry workers would use picks and chisels to tunnel a narrow gallery beneath the freed block, carefully working to separate it from the bedrock below. They would leave temporary pillars of stone to support the immense weight until they were ready to lower it. Then, using levers, they would break these last supports, allowing the block to settle onto a bed of prepared sand or logs. This entire operation, from the initial drilling to the final undercutting, required a deep, intuitive knowledge of the stone itself. Experienced quarrymen could read the rock, identifying hidden flaws, veins of different hardness, and the direction of the natural grain. Their expertise ensured a high yield of usable material and minimized the terrifying risk of an uncontrolled collapse that could destroy months of work and crush the workers beneath thousands of tons of stone. The quarry tunnel, therefore, was not a passage to a hidden treasure, but the birthplace of the treasure itself. It was the starting point for the grand monuments that defined an era, a place where patient, precise labor and a masterful understanding of nature's forces conspired to literally shape the visible glory of Rome. For all their mastery over stone and water, the Romans faced an invisible adversary in their tunnels that was just as relentless and far more insidious: the very air they breathed. Ventilation was not a secondary concern, it was a daily, life or death calculation. In the cramped, lamp-lit galleries deep beneath the earth, the atmosphere could turn from life-sustaining to lethal in a matter of moments. The primary killers were a silent trio: carbon dioxide from the miners' own exhalations, carbon monoxide from their smoldering oil lamps, and in certain rock layers, pockets of naturally occurring gases like hydrogen sulfide or methane, which could seep from the walls without warning. A miner might be swinging his pick one moment, and after taking a single breath of foul air, collapse unconscious, his lamp flickering out as the oxygen vanished. The greatest terror was that these gases were often undetectable until it was too late, giving no smell or visible sign before they suffocated a man where he stood. Their primary defense against this atmospheric prison was a clever application of basic physics, using the earth itself as a giant breathing apparatus. The key was the strategic use of vertical shafts, known as puttae or light wells, which we've mentioned in the context of surveying and light, but their most vital function was to act as a passive ventilation system, creating a natural draft through convection. Here's how it worked. The air deep inside a tunnel, heated by the workers' bodies and their lamps, would become warmer and less dense. This warm, stale air would naturally rise. When it reached a vertical shaft, it would rush upwards toward the cooler, fresher air at the surface. This rising column of air created a vacuum, pulling cooler, oxygen-rich air in from the tunnel's main entrance or from other shafts, effectively creating a continuous, gravity-powered circulation system. The placement of these shafts was a science in itself. Engineers would space them at calculated intervals along the tunnel's route, ensuring that no section was too far from a source of fresh air. In complex, multi-level mines, they would design the entire network like a subterranean circulatory system, with some shafts dedicated to drawing fresh air in and others acting as exhaust chimneys for the foul air, preventing deadly cross-currents and dead zones. Yet this elegant system had its limits, and when it failed, the consequences were swift and brutal. In long, deep tunnels where the natural draft was weak, or in pockets away from the main airflow, toxic gases and dust could accumulate to deadly concentrations. The miners themselves became the most sensitive instruments for detecting these dangers. They developed a profound, instinctual relationship with their oil lamps, watching the tiny flame with the focus of a surgeon. A flame that burned unusually low, flickered erratically, or changed color from a healthy yellow to a weak, blue-tinged ghost was the most urgent alarm bell possible. A dimming lamp signaled a dangerous buildup of carbon dioxide. A flame that suddenly extinguished meant oxygen levels had plummeted to a point incompatible with life. This visual cue was often the only warning they had to drop their tools and scramble for the surface before they were overcome. It was a constant, nerve-wracking dialogue with an unseen enemy, where a flicker of light was the difference between life and a suffocating death in the dark. Beyond the immediate threat of poisonous gases, the miners battled a slower, more insidious killer: rock dust. Every swing of a hammer, every chip of a chisel, filled the stagnant air with a fine, abrasive powder. In tunnels cutting through sandstone or quartzite, this dust was primarily silica. With no protective masks and limited airflow, miners inhaled this microscopic debris with every breath. Over months and years, these sharp particles embedded themselves deep in lung tissue, causing inflammation, scarring, and a debilitating condition we now know as silicosis, or miner's lung. The Romans may not have had a medical name for it, but they certainly recognized the symptoms: a persistent, racking cough, shortness of breath, chest pain, and a gradual, wasting decline as the victim's lungs turned to stone, effectively suffocating them from the inside out. This was a death sentence delivered in slow motion, a cruel trade for a day's wages, ensuring that even those who survived cave-ins and gas attacks would rarely live to see old age. The human cost of this battle for breath is written in the sparse, grim records that have survived. While we lack precise statistics, accounts from historians like Pliny the Elder and Diodorus Siculus describe the appalling conditions and short life expectancies for those condemned to work in the mines and deep tunnels. For the slaves, prisoners of war, and convicted criminals who formed the bulk of this labor force, a tunnel was less a workplace and more a subterranean gas chamber where death could come instantly from a pocket of methane or gradually from a lungful of dust. Their high mortality rate was simply factored into the economic calculus of the operation. They were a disposable resource, as replaceable as a broken pickaxe. This stark reality forces us to view these engineering marvels in a more somber light. The same ingenuity that carved perfect arches and harnessed water wheels also accepted a horrifying level of human sacrifice. The cool, stable air of a completed aqueduct tunnel, which would flow with clean water for centuries, was paid for with the last choked breaths of countless unnamed workers, their lives extinguished in the oppressive, silent dark so that the empire above could breathe easier. Ensuring that two teams of miners, starting miles apart and digging through solid rock, would meet in perfect alignment deep underground stands as one of the most breathtaking demonstrations of Roman technical prowess. This was not a hopeful gamble. It was a mathematical certainty achieved through a rigorous process of triangulation and leveling that transformed the chaotic landscape into a precise, measurable grid. At the heart of this operation was the groma, the fundamental surveying instrument that allowed engineers to project perfectly straight lines across any terrain. The process began long before the first pickaxe struck stone. Surveyors would first establish the tunnel's intended endpoints on the surface. Then, using the groma, they would create a series of interconnected right-angle turns, effectively walking a straight line over hills and around valleys. Imagine a surveyor on a hilltop, sighting along the weighted plumb lines of his groma to a distant marker held by an assistant. Once that line was established, he would turn the instrument 90 degrees to set a new perpendicular line, moving the entire team laterally before turning again to continue the original direction. This process of leapfrogging with right angles created a visible surface track that precisely mirrored the intended path of the tunnel far below, no matter how uneven the ground above might be. But a straight line was only half the battle. The true genius lay in maintaining a consistent, gentle gradient, especially for aqueduct tunnels where the water's flow depended on a perfectly calculated slope. This is where the chorobates became indispensable. This long, wooden leveling bench, often 20 feet in length, was the most accurate tool in their arsenal for determining elevation. The surveyor would set up the chorobates and fill its central groove with water. The still, flat surface of the water gave him a perfect horizontal reference. By measuring the height of this water level at one point and comparing it to a measuring rod or gratis at a distant point, he could calculate the exact difference in elevation between the two spots. To establish the tunnel's gradient, they would perform this painstaking process over and over again, marching the course of the proposed tunnel mile by mile. They'd record a continuous elevation profile of the entire route, ensuring that the final design called for a steady, unwavering drop of perhaps just 1 foot every several hundred feet. This meticulous surface mapping was the project's Bible. Every depth measurement and digging instruction for the team's underground would be derived from this initial topographical survey. The critical link between this surface map and the subterranean diggers was the network of vertical shafts, the pudae. These were not random holes, they were carefully positioned navigational anchors. Along the straight surface line established by the groma, crews would sink these shafts at regular intervals, digging straight down until they reached the precise elevation where the tunnel was supposed to be. Reaching the correct depth was a feat in itself. Surveyors would lower predetermined lengths of rope or use calibrated poles to ensure the bottom of each shaft was exactly at the grade level established by the chorobate survey. Once a shaft was complete, it became a hub of activity and a crucial point of verification. Miners would begin digging outward from the bottom of the shaft in both directions, following the tunnel's planned course. Critically, surveyors could now descend into the shaft and use a simpler version of the chorobates or a water level to check that the tunnel floor was being dug at the correct slope. They could also use hanging plumb bobs and sighting lines within the tunnel itself to ensure they were maintaining a straight path between shafts. This system transformed an impossibly long, dark tunnel into a series of shorter, manageable segments, each one constantly checked and corrected against the master surface plan. The moment of truth came when the two advancing tunnel faces were close enough to hear each other's hammer blows echoing through the rock. Even with all their precautions, the final connection required incredible finesse. The sound of the other team guided them, but the final alignment was a matter of geometry and faith. The surveyor's records show they were prepared for minute corrections. If the two headings were slightly misaligned, they would intentionally adjust the course of one or both to create a gentle, curved connection rather than a jarring, abrupt shift. The success rate was astonishing. Consider the Piscina Mirabilis, a massive Roman reservoir where the feeder tunnels driven from different directions meet with an alignment error of just a few inches over a distance of hundreds of feet. Or the aqueducts feeding ancient Nemesis, modern-day Nims, where the tunnel gradients are so consistently precise that the water flow would have been perfectly smooth and efficient. This mathematical mastery, achieved with tools that seem rudimentary to us, underscores a fundamental Roman belief that the natural world, for all its apparent chaos, could be understood, measured, and ultimately commanded through the disciplined application of number, line, and level. They didn't just build tunnels, they inscribed the principles of geometry onto the very fabric of the earth, creating a hidden architecture of such exactitude that it continues to baffle and inspire engineers to this day. For all their mathematical precision and engineering genius, the Romans were not immune to catastrophe. The dark, pressing reality of a tunnel collapse was a constant specter hanging over every project, a sudden and violent reminder that the earth could reclaim its own in an instant. We have to imagine the scene, the rhythmic tapping of hammers suddenly replaced by an ominous, deep groaning from the tunnel ceiling. A shower of dust and small stones rains down, followed by the sickening crack of splintering timber support. Then, a deafening roar as a section of the roof gives way, swallowing men, tools, and months of back-breaking labor in a chaotic avalanche of rock and soil. In the choking dust and silence that followed, the scale of the disaster would become clear. A section of tunnel, perhaps hundreds of feet long, now completely blocked by an impassable mound of debris, with the grim possibility that workers were trapped on the other side. These were not mere setbacks, they were human and economic tragedies that could bankrupt a project and shatter the reputation of the engineers behind it. So what typically caused these structural failures? The reasons were as varied as the geology they worked through, but a few common themes emerged from historical analysis. One of the most frequent culprits was a simple miscalculation of the ground conditions. A survey might indicate a stable layer of tough rock, but the tunnel could unexpectedly hit a hidden pocket of water-saturated sand or loose gravel, material that would flow into the opening like liquid the moment it was disturbed, overwhelming any timber shoring in second. Another common failure was overbreak, where miners, in their zeal to progress quickly, excavated a wider chamber than originally planned, creating a ceiling span that was too wide for the rock to support itself, even with arches. The immense, uneven pressure from above would eventually find the weakest point, often a joint in the brickwork or a slightly rotted timber, and trigger a chain reaction collapse. Water was another relentless enemy. A persistent, unnoticed seepage could gradually soften the clay surrounding a tunnel, lubricating the rock layers and turning a stable wall into a sliding mass of mud and stone, a phenomenon known as a shear failure. When such a disaster struck, the Roman response was likely a blend of practical investigation and grim accountability. The lead engineer, the architectus, would have been summoned to the site to conduct a formal inquiry. His first task would be a visual examination of the collapse zone, looking for telltale signs in the debris, where the timber supports shattered or simply bent. If they were splintered, it suggested a sudden, massive impact from above, perhaps a large, unstable rock ledge that had gone undetected. If they were bowed and crushed slowly, it pointed to a gradual, creeping pressure from the sides, indicating that the walls themselves were unstable. He would examine the fracture patterns on the fallen rock, looking to see if it had broken along clean, natural lines, or if it was a crumbly, weathered material that should never have been trusted. He would also interview the surviving foremen and workers. Had they heard unusual creaking in the hours before? Had there been an increase in water seepage or minor rock falls? These eyewitness accounts were crucial data points in a world without forensic science. The lessons learned from these failures were hard-won, but were systematically incorporated into future engineering practice. A collapse caused by unstable soil likely led to the more widespread and careful use of backfilling, where the engineered tunnel was packed in gravel to evenly distribute the surrounding pressure. A failure due to weak rock might have resulted in a new rule of thumb for the spacing of support arches, mandating they be placed closer together in certain types of stone. There's compelling evidence that they developed a kind of empirical safety factor. For instance, if a calculation showed that a wall needed to be 3 feet thick to hold a certain load, they might build it 4 or 5 feet thick, adding a margin of error that accounted for the unpredictable nature of the earth. This iterative process, build, fail, investigate, and improve, was the true engine of Roman engineering progress. It wasn't just about brilliant successes, it was about learning from devastating failures, and each collapse, tragic as it was, contributed a piece of hard-earned knowledge that made the next tunnel that much safer, stronger, and more likely to stand for millennia. No place on Earth offers a more intimate or heartbreakingly vivid portrait of Roman subterranean life than the cities frozen in time along the Bay of Naples. When Mount Vesuvius erupted in the year 79, its layers of volcanic ash and superheated gas did more than simply destroy. They performed a miraculous act of preservation, sealing entire cities in a protective shell. While we often focus on the poignant casts of the victims or the stunningly intact frescoes on the walls above, it's beneath the streets of Pompeii and Herculaneum that we find a perfectly preserved blueprint of Roman underground engineering in daily practice. These cities were not just surface settlements. They were living, breathing organisms with deep roots, and the volcanic cataclysm captured their hidden veins and arteries in a state of suspended animation, granting us an archaeological window unlike any other. In Pompeii, the most immediately striking underground features are the ubiquitous cellars and storerooms that lay beneath nearly every wealthy home and commercial establishment. Descending the steep stone stairs into a Pompeian cella veneria or wine cellar is like stepping directly into the past. The volcanic ash filled these spaces completely, protecting their contents from looters and the elements for centuries. Archaeologists have uncovered rows of massive ceramic jars, called dolia, still embedded in the ground where they were used to ferment and store wine, olive oil, and garum, the pungent fish sauce beloved by Romans. The environment in these cellars was crucial. The thick, earth-sheltered walls and semi-subterranean design provided a naturally cool and stable temperature, an ancient form of climate control essential for preserving perishable goods. In one famous bakery, the underground storeroom was found filled with petrified loaves of bread, carbonized by the intense heat but still bearing the baker's stamp, a snapshot of a business interrupted at its most fundamental level. These spaces reveal the profound Roman understanding of using the earth as a practical resource, integrating it directly into their commercial and domestic economies. Herculaneum, buried by a different, denser pyroclastic material that carbonized organic matter, offers an even more detailed glimpse, particularly of the humble, everyday tunnels that serve the common people. While Pompeii shows us the grander townhouses, Herculaneum preserves an incredible network of underground shops and workshops. Beneath the sidewalks and in the foundations of apartment blocks, small, tunnel-like rooms housed everything from textile dyers to metal workers. In one remarkable discovery, a small underground room was found containing a wooden bed, a small cabinet, and the carbonized remains of a ladder, suggesting it served as both a workshop and a cramped living quarters for a laborer or a slave. This blurring of lines between workspace and home, all contained within a carved-out subterranean chamber, speaks volumes about the social stratification of Roman life. For the elite, the underground was for storage and luxury. For the lower classes, it was often the very space in which they lived and worked, a hidden world of industry tucked just out of sight of the elegant streets above. The water systems of these cities are another marvel of preserved subterranean infrastructure. Pompeii's streets are lined with sturdy stone sidewalks, and beneath them runs a sophisticated network of underground water channels and lead pipe. The city was supplied with fresh water from an aqueduct, which fed a large central holding tank, the Castellum Aquae. From this distribution point, the water was channeled through a system of underground lead pipes to public fountains on street corners, to the lavish bathhouses, and into the homes of the wealthy. The eruption captured this system in a state of active use. Excavations have revealed the pipes still in place under the streets and even inside the walls of homes, with their stopcocks and junctions showing exactly how water pressure was managed and directed. In the final, frantic hours before the city was buried, engineers were even caught in the act of performing maintenance. In one tunnel, tools were found beside a section of disassembled pipe, a silent testament to a repair job that would never be finished. This level of detail shows us that Roman urban utilities were not static, but dynamic systems requiring constant, skilled attention. Perhaps the most emotionally resonant underground spaces are the cryptoporticus passages found in the larger villas of both cities. These semi-subterranean galleries, which we discussed earlier as places of cool retreat and political intrigue, are preserved here with stunning clarity. At the Villa of the Papyri in Herculaneum, a magnificent cryptoporticus stretches for hundreds of feet, its walls still bearing the soot from the oil lamps that once illuminated it. Walking through it today, you can experience the exact quality of light and shadow its designers intended, the way the arched openings filter the sun, creating a cool, dimly lit world of echoing footsteps that feels entirely separate from the heat and bustle of the surface. In Pompeii, the Villa of the Mysteries boasts another stunning example, its cryptoporticus offering framed views of the garden while providing a perfectly shaded promenade. The preservation of these spaces allows us to understand them not just as architectural blueprints, but as experiential environments. We can feel the temperature drop, hear the acoustics change, and understand how the Roman elite used this sophisticated underground architecture to manipulate their environment and control their social interactions, creating a private world of comfort and secrecy just a few steps beneath their sun-drenched courtyards. Ultimately, the tunnels of Pompeii and Herculaneum provide something that no textbook or reconstructed model ever can: a direct, tangible connection to the daily rhythm of Roman life. They are a time capsule that captures not just the grand achievements, but the mundane realities. We see the wine merchant cellar stocked for the season, the baker's grain stored for the next week's bread, the plumber's tools left in a half-finished repair, and the slave's humble bed in a cramped underground room. This is the true legacy preserved in lava and ash. It shows us that the Roman mastery of the underground was not a monolithic imperial project, but a versatile and deeply integrated practice that touched every level of society, from the emperor in his palace cryptoporticus to the common laborer in his workshop cellar. These cities remind us that history is not only written in the stones of colosseums and temples, but also in the silent, enduring spaces carved beneath the earth, where the most intimate details of a civilization were waiting, perfectly preserved, for the future to uncover. The principles and techniques perfected in the heart of Italy did not remain there. They traveled with the legions, the administrators, and the traders, replicating Rome's hidden infrastructure across the vast expanse of the empire. One of the most spectacular examples lies far to the east, in the city that would become the second Rome, Constantinople. To secure a water supply worthy of an imperial capital, engineers undertook one of the most complex hydraulic projects of the ancient world. They constructed a system of aqueducts and tunnels stretching over 250 kilometers from the forested hills of Thrace. But the final approach to the city was the true masterpiece. The most famous of these, the Aqueduct of Valens, is celebrated for its soaring double-tiered arches marching through the modern cityscape, yet its most critical section is the one you cannot see. To maintain the crucial gradient and cross the final hills before the city, Roman engineers carved a subterranean channel 5 kilometers long, known as the Byzantine conduit. This was not a simple ditch. It was a meticulously engineered tunnel, wide enough for a person to walk through, lined with waterproof mortar, and punctuated by dozens of maintenance and ventilation shafts that dropped over 100 feet down to the channel below. This hidden artery ensured that Constantinople, a city of hundreds of thousands, could thrive on a peninsula with limited natural water sources, a direct application of Italian engineering logic to a new and demanding environment. Venture northwest to the rugged landscape of Roman Britain, and you find a different kind of subterranean ambition, driven not by urban luxury, but by military necessity and economic hunger. At the Dalhousie gold mines in Wales, the Romans encountered a challenging environment of hard shale and slate. They immediately applied their signature hydraulic mining techniques on a dramatic scale. They constructed massive storage reservoirs high in the hills, then channeled the water through a network of leats or artificial channels to unleash it against the hillsides in a controlled deluge, stripping away the overburden to reveal the gold-bearing ore beneath. But their ingenuity went further. To reach deeper deposits, they sank vertical shafts and drove horizontal adits or drainage tunnels deep into the rock. One of their most astounding feats here was a tailrace tunnel designed to dewater an open cast mine. They carved this passage for over 1.5 kilometers through solid rock, ensuring it had a consistent, gentle slope so that water would flow out by gravity, allowing miners to work the pit floor. The scale of this operation, in a cold, wet, and remote province, demonstrates how quickly and systematically Roman engineering knowledge could be deployed to extract wealth from the very edges of their domain. In the sun-baked provinces of North Africa, where water was more precious than gold, Roman tunneling expertise became the foundation of agricultural prosperity. The semi-arid regions in what is now Tunisia and Libya were transformed into the breadbasket of the empire through an ingenious adaptation of a local technology, the canat or fragara system. The Romans encountered these subterranean water harvesting tunnels, originally developed in Persia, and refined them with their own engineering rigor. The principle was brilliant in its simplicity. On a sloping plain, crews would dig a series of vertical shafts at regular intervals, connected at the bottom by a gently sloping tunnel. This tunnel would tap into the water table at the foot of a mountain range and channel the groundwater over many kilometers, entirely by gravity, to the fields and settlements on the plains. The vertical shafts provided access for construction and maintenance, and crucially, they allowed the excavated spoil to be removed, creating the characteristic lines of crescent-shaped spoil heaps that still scar the North African landscape today. By applying their surveying skills with the groma and chorobates to ensure the perfect, consistent slope of these tunnels, the Romans amplified an existing technology, turning sporadic desert oases into a continuous, reliable irrigation network that supported vast olive groves and wheat fields for centuries. Perhaps one of the most visually striking examples of Roman tunneling endurance can be found not in a mine or an aqueduct, but in a road tunnel in modern-day Turkey. The Tunnel of Titus, built in the 1st century, is a remarkable monument to sheer persistence. Facing a treacherous coastal cliff on the road between the cities of Seleucia and Siedra, Roman engineers chose the most direct and permanent solution. They drove a tunnel straight through the mountain. Stretching for over 130 meters, the tunnel is a clean, arched passage that still bears the clear, precise marks of the pickaxes and chisels that carved it. What makes it extraordinary is the evidence of the construction process itself. The ceiling is pockmarked with small, square sockets, which held the wooden beams for the scaffolding and centering used by the masons as they vaulted the ceiling. The tunnel's floor still shows the ruts worn by countless cartwheels over centuries of use. This is not a project for glory, but for pure, pragmatic utility, a testament to the Roman insistence on creating permanent, all-weather infrastructure to bind their empire together, even if it meant moving a mountain to save a few miles of dangerous coastline. This diffusion of knowledge was not a one-way street from Rome to the provinces. The empire acted as a vast information network, where techniques developed in one corner could be tested, refined, and then applied elsewhere. An engineer who learned the complexities of dewatering in the silver mines of Spain might later supervise the construction of a drainage adit in Wales. A surveyor who mastered the gentle gradients for aqueducts in Gaul could bring that expertise to the water channels of North Africa. The Roman army was the primary vector for this exchange. Legionaries, many of whom were trained as combat engineers, would be deployed from one end of the empire to the other, taking their practical skills with them. They built the same kinds of forts, with the same hidden drainage systems and storage cellars, from the Syrian desert to the Scottish border. This systematic transfer of technology created a recognizable Roman footprint underground, a hidden layer of engineering consistency that underlay the diverse cultures and landscapes of the empire. It proves that Rome's greatest strength was not just its legions or its laws, but its ability to standardize and replicate complex engineering solutions, creating a unified infrastructure that allowed a city in Turkey, a mine in Wales, and a farm in Tunisia to all operate on the same principles of subterranean mastery, binding the empire together from the ground down. The legacy of these ancient builders extends far beyond the silent, dusty ruins we explore today. It flows directly into the very bedrock of our modern world, shaping the tunnels that carry our trains, channel our water, and power our cities. The principles Roman engineers established through sheer empiricism and brilliant intuition form a continuous thread in the story of human excavation, a story where we are still, in many ways, following the path they first carved. Consider the most iconic symbol of Roman subterranean strength, the arch, that simple, powerful shape, which channeled immense gravitational forces outwards to stable abutments, is not merely a historical artifact. It is the fundamental principle behind the vast, cathedral-like spaces of modern metro stations and the cavernous highway tunnels that plunge through mountains. While we now reinforce our arches with steel and concrete, the core structural logic remains unchanged. The Roman understanding that a curved roof is inherently stronger than a flat one, a lesson they learned through a triumph and collapse, is a foundational axiom taught to every civil engineering student on the planet. Their brick-vaulted aqueduct channels were the direct ancestors of the concrete line bores that house high-speed rail lines today, both designed to manage tremendous overhead pressure for centuries. This influence is equally profound in the relentless, age-old battle against water. The Romans were the first civilization to tackle groundwater on an industrial scale, and their solutions were breathtakingly prescient. The Archimedes screw, which they deployed so effectively in the depths of Spanish mines, is not a relic. You can find virtually identical screws, now powered by electricity instead of human labor, in wastewater treatment plants and agricultural irrigation projects across the globe, still moving thick, silt-laden water with an efficiency that modern technology struggles to improve upon. Their network of drainage channels and sump pits, designed to keep tunnel floors dry, is the direct precursor to the dewatering systems used in every major construction project that digs below the water table. Before breaking ground on a new subway line, engineers still conduct extensive hydrogeological surveys, a highly advanced version of the Roman practice of observing vegetation and soil types to predict groundwater, and their plans always include a detailed strategy for continuous pumping, a direct echo of the relentless work of those Roman water wheels. Even the very process of planning a tunnel's route owes a deep debt to Roman methodology. The meticulous surveyors with their gromas and chorobates were creating the first true topographical maps, translating a three-dimensional landscape into a set of precise instructions. Today, we use GPS, laser theodolites, and satellite imaging, but the ultimate goal is identical: to establish a straight line and a consistent grade between two distant points. The Roman technique of sinking vertical shafts along a tunnel's proposed path to verify alignment and depth is the conceptual forerunner of modern pilot tunneling and directional drilling. Before a massive tunnel boring machine begins its work, engineers often first drill a small, exploratory pilot hole to confirm the geology and the accuracy of their surveys, a direct reflection of the Roman practice of using puttae to ensure their teams digging from opposite sides of a mountain would meet perfectly in the middle. The Roman commitment to meticulous pre-planning set a standard that defined engineering as a disciplined profession, moving it from guesswork to a predictive science. Perhaps the most telling sign of their enduring impact is found not in our machinery, but in our ongoing dialogue with their work. Modern engineers and geologists still actively study Roman tunnels as long-term stability experiments. These ancient structures have been bearing loads and resisting groundwater for 2 millennia, providing invaluable real-world data on how materials and designs behave over timescales impossible to replicate in a lab. The exceptional durability of their pozzolana-based concrete, which actually grows stronger underwater, has sparked intense modern research. Scientists have only recently begun to fully decode its complex chemical microstructure, hoping to reverse engineer a recipe for more sustainable and resilient modern concrete. The tunnels themselves are seen as case studies in how to build for the ages. When engineers assess the potential lifespan of a new underground repository for nuclear waste, designed to remain intact for tens of thousands of years, they look to the Roman tunnels that have already endured for 2,000 as a benchmark of success, a testament to a building philosophy that prioritized permanence. This enduring legacy reveals a profound truth about human progress. The transition from the Roman dalabra to the modern tunnel boring machine is not a story of replacement, but one of evolution. We have amplified our power with fossil fuels and digitized our precision with computers. But the fundamental challenges of moving Earth, managing water, and supporting voids remain the same. The Romans provided the foundational toolkit of ideas: the arch, the screw, the water-resistant cement, the surveyed line. We have spent the centuries since refining their innovations, scaling them up, and giving them new power. To walk through a Roman aqueduct tunnel is to stand in the prototype for the infrastructure that defines our contemporary world. It's a humbling reminder that our greatest modern achievements often rest on principles discovered in the flickering lamp light of ancient passageways, where visionary engineers first learned to negotiate with the earth, leaving a blueprint for the future written in stone and mortar. So as our journey through this hidden world comes to a close, we're left with an overwhelming sense of admiration for the sheer human endeavor it represented. This was not the work of magic or mythical giants, but of countless thousands of ordinary people whose names are lost to history, applying extraordinary intelligence and relentless labor to a problem of monumental scale. They descended into the earth with little more than iron, fire, and wooden tools, armed with a geometric understanding of their world that allowed them to conquer darkness, water, and the immense pressure of the stone above them. The Roman underground is a testament to a unique fusion of mind and muscle, where the brilliant calculations of the architectus were given physical form by the calloused hands of legionaries, slaves, and fossors, who paid for these wonders with their health, their freedom, and often their very life. It was a collaboration across social strata, a symphony of coordinated effort that resonates through the centuries. When we step back and view the subterranean network in its entirety, we see that it was far more than a collection of impressive holes in the ground. These tunnels were the hidden arteries of the empire, a vital circulatory system that pulsed with the lifeblood of water, wealth, and power. The aqueduct channels ensured the health and grandeur of mighty cities. The mines pumped precious metals into the economy to fund armies and ambitions. The military passages decided the fate of sieges, and the cryptoporticus corridors allowed the political machinery of the elite to operate in shadow. Just as a human body cannot survive without the veins and arteries hidden beneath the skin, the Roman Empire could not have functioned, expanded, or endured for centuries without this deeply buried infrastructure. The glorious temples, bustling forums, and triumphant arches that we traditionally associate with Rome were merely the visible, public face of the empire. Its true, enduring strength was forged in the cool, dark silence beneath the earth. This legacy challenges us to expand our very definition of ancient achievement. We rightly marvel at the pyramids of Giza or the Parthenon, structures that reach for the heavens. But the Romans teach us that true greatness can also be found by looking down, by mastering the realm beneath our feet. Their vision was three-dimensional. They built not only upwards in spectacular displays of power, but also downwards in profound acts of utility and foresight. They understood that the most critical foundations for a civilization are often the ones you cannot see. In an age before steam power, electricity, or digital sensors, they displayed a level of planning, persistence, and practical genius that remains difficult to fully comprehend. They left us a powerful lesson that the measure of a society's advancement is not just in its most dazzling monuments, but in the resilience and intelligence of the systems that support daily life, systems that often operate best when they are out of sight. The story of these tunnels is ultimately a deeply human one. It's a narrative of ambition pushing against the limits of the possible, of creativity flourishing in constraint, and of an unwavering drive to reshape the world according to a grand, logical design. Every soot-blackened ceiling, every pick mark on a wall, and every perfectly laid brick arch is a message from the past, a whisper from the miners, surveyors, and masons who dared to carve order from chaos. Their work invites us to see history not as a series of dry dates and battles, but as a tangible, physical reality that we can still walk through and touch, a reality built by people not so different from us, who faced impossible challenges and left behind solutions that continue to inspire awe and humility. Now, we'd love to hear which part of this hidden world captivated your imagination the most. Was it the terrifying claustrophobia of a military siege mine, where the fate of a city was decided in a dark, underground battle. Or perhaps the serene, orderly silence of the aqueduct tunnels, where water still flows along gradients calculated 2,000 years ago. Maybe you're fascinated by the poignant beauty of the catacombs, where a persecuted community found both a final resting place and a sanctuary for their faith. Let us know in the comments below which Roman tunnel mystery you find most compelling. Your thoughts help us all see these ancient wonders through new eyes, continuing the conversation about one of the most ingenious and determined civilizations the world has ever known.